let us have a look at this question based on stack. When you look at this question, let me tell you, you're going to get an impression that it is a lengthy question, right? But believe me, it is just a lengthy question. It is not a complicated question. Only the thing is, we should be able to understand the details that are given in the question. Then we will use those details to solve this question. One basic idea about this question is, whenever you're trying to solve any lengthy question, my humble urge for you people is to first of all identify the question, the actual question, and then you again give yourself some time to read this question. So that means we'll completely look at this question and we will track the actual question. Okay, so when you look at this question, finally the question asked here is, after the execution of the call instruction, the value of the stack pointer. Here we are asked about what is the final value of the stack pointer. This is the question. This is the final question. Okay, now whenever you have come across these kind of a lengthy questions, what you do is you just track the final question, after which then you go ahead in reading the question. Then you will get an idea how to solve such kind of a questions. Okay, now let us read this question. Once again, this question is based on stack. Okay, I request you people to go through the sessions of the stack once again. Anyhow, as you people heard about the stack sessions, now it is the right time to solve a question which is based on stack. Now let us see. Consider a processor with a byte addressable memory. Assume that all the registers, including program counter, PC, and the program status word, PSW, are of size 2 bytes. Okay, here the details are. First thing is the memory is byte addressable. Okay, now let us list out these details that are in the question. Memory is byte addressable. The first detail that we got. Okay, and then next thing is, assume that all the registers, including program counter and the program status word, are of size 2 bytes. Okay, if the register size is equal to 2 bytes, one memory word size is also equal to 2 bytes. One word in main memory is equal to 2 bytes. Okay, right? Fine. That is the next detail what we got. One word is equal to 2 bytes, which is equal to 16 bits. A stack in the main memory is implemented from the memory location 0100 hexa. Of course, he is talking about a memory stack, right? There are two kinds of stacks. One is a register stack, another one is a memory stack. The register stack is a CPU stack which is implemented in the CPU. Memory stack is a memory stack which is implemented in main memory. Here, he is talking about a memory stack which is implemented in the main memory, which is originated from 0100. That is, stack is organized. Stack is implemented in the main memory. The base of the stack is 0100. From this location, the stack is designed and organized. Okay, the stack origin is 0100. Okay, this is the important additional detail regarding the stack. Okay, and the stack pointer points to the topmost element of the stack. Of course, we know that. The current value of the stack pointer is 016E, meaning there is a current top of the stack. This is the current top of the stack, 016E, in which there is an element. Okay, what stack pointer shows? The stack pointer holds an address in which the topmost element of the stack is present. That is, the stack pointer is going to hold the address of the topmost element of the stack. That's it. Okay, now the call instruction is of two words. The first word is the opcode and the second word is the starting address of the subroutine. the call instruction is implemented as follows. That is, he's talking now about the implementation of the call instruction. You know that the call instruction is going to branch to a subroutine. If you could remember our BSA instruction, what is BSA? BSA is nothing but the call instruction. What is BSA? When you talk about BSA, we will branch to the subroutine address, right? For an example, there is something called call 250. Okay. Now this instruction is available at a memory location called 46. Okay. Now there is a program counter value, maybe 47. The program counter value, whatever the next address, that is the program counter value. And now whenever there is a call instruction, we will be branching to 250, in which there is a subroutine. But before we branch to this 250, we should be able to save this program counter value. Where we are going to save this program counter value? We are going to push this program counter value into the stack, right? We're going to push this program counter value into the stack before we branch to the subroutine. Subroutine's address, which is specified in the address part of the instruction. Okay, so here he is giving such detail again. He is giving the detail again. The call instruction is implemented as follows. When the call instruction gets executed, store the current value of the program counter into the stack. Store the value of the PSW register into the stack. That is, whenever a call instruction is implemented, is executed, there will be two elements pushed into the stack. Okay, the stack will be loaded with two elements. Stack will be loaded with, the first one is the program counter, then the next one is the PSW, which is also called as the flag register of a system. Okay, so whenever a call instruction, that means whenever a routine calls a subroutine, the fundamental business of this routine is to store the current value of the PC into the stack. Okay, so when a call instruction gets executed, two elements will get pushed into the stack. One is the value of the program counter, one more is the value of the PSW into the stack. That is, when call instruction is executed, the stack will be added with two elements. One is PC, one more is PSW. Okay, now the question is, the contents of the program counter just before the fetch of a call instruction is 5FA hexa, which is given in hexa. Now just look at the question, what is asked. After the execution of the call instruction, what is the value of the stack pointer? Once after the call instruction is executed, what will be the value of the stack pointer? That is the question. The simple thing is, go to the current value of the stack pointer. This is the current value of the stack pointer, right? Now, whenever a call instruction is executed, this stack is added with two more elements. That is, now on the topmost element, there is one more element pushed into the stack, that is program counter, the program counter value of the routine, which is calling another routine. On the top of the program counter, PSW, which is a flag register, will also get pushed. That is, whenever a call instruction gets executed, the stack will be pushed with two more elements. Now, what is the value of the stack pointer? Stack pointer is equal to, SP is equal to SP plus 1, because here it is given that it is an upward stack. Okay, the stack is implemented from memory and it grows upward. It's an upward stack. You know what is the difference between upward stack and a downward stack? Upward stack increments the program stack pointer during a push operation. Downward stack decrements the stack pointer during a push operation. But it grows upwards. There's no problem. Okay, now stack pointer will be equal to SP plus 1 when one element is pushed, and the stack pointer will be equal to SP plus 2 when two elements are pushed. Okay, then now let us have a look at SP is equal to SP plus 1 after program counter. Then one more element is pushed, that is SP is equal to one more time, it will get incremented. SP is equal to SP plus 1 as PSW also gets pushed, right? But here, there is a small change in this, because since the memory is byte addressable, one word is equal to 2 bytes, right? Okay, so the program counter, bigger pardon, the stack pointer, every time it gets updated as SP plus 2. When a push operation gets performed, one value will get pushed into the stack. Now from this address to the next address, the stack pointer will get incremented, right? So one address is equal to one word is equal to 2 bytes. So 2 bytes gets 2 addresses, right? Since one word is equal to 2 bytes and every byte will be given an address in the main memory. Okay, so in order to go from this location to this location, the stack pointer should be incremented with 2. So one element is pushed into the stack. SP is equal to SP plus 2 since the memory is byte addressable. Okay, as there are 2 elements pushed, SP is equal to SP plus 2 for program counter. SP is equal to SP plus 2 more, having PSW pushed into the stack. So the final value of the stack pointer is, let me write it here, SP is equal to SP plus 4. Okay, so now we'll calculate SP is equal to SP plus 4. The current value of the stack pointer is 016E as given in the question. When we convert it into binary, 0000, this 1 is 0001, this 6 is 0110, this E is 1110. This is the equivalent value of this hexadecimal value in a binary. Okay, because every digit will have a corresponding 4 digits. Now, SP is equal to SP plus 4. This stack pointer value, a 4 should be added to the stack pointer value. We will add a 4 here. 0100 is 4 in binary. So we will add now 00, 0, 1 0, 1, 1 1, 0, 1 1, 0 1. Okay, and this is 1 1 1 0, and this will not get changed. 0 0 0 1, and this is also simply 0 0 0 0. Now the final value of the stack pointer is, this is 0. The equivalent hexadecimal value is 0. This binary, the hexadecimal value is equal to 1. The 0111 is 7 in hexa. 0010 is 2 in hexa. Okay, which is 16. So SP is equal to 0172 hexa. This is the final answer. This is how you're going to solve a complex question, rather, a lengthy question in a simple way. The first thing is, the first and fundamental rule whenever you look at a lengthy question is, first you track down the question. Where is the question exactly? The question is here. What is the value of the stack pointer? Now you write it down. Then you track back. You just list out the details which are given in the question and use them appropriately for solving the question. This is how you're going to make a complex or a lengthy question simple.